Well, looking at these standard reduction potential tables is always, not always, in the beginning confusing. Because what are we trying to say? We have these referenced values for the measuring some kind of likeliness or spontaneity of a reduction reaction. I think because there are different ways to teach it, that there are different ways to think about it, and I hate to be egocentric, but if you think about it my way, this always does me well. So if you think about it my way, I think it'll, eventually with enough practice, you'll find, oh yeah, that makes a little bit of sense. So all these reduction potentials are measured relative to kind of a funky setup where I have a platinum unreactive piece of metal submerged in some HCl, 1 molar HCl. It's touching the aqueous HCl, but it's also in contact with some hydrogen gas being fed into the chamber. And so the hydrogen gas bubbles up in and around where it contacts the HCl and also in contact with the platinum. But the platinum doesn't partake in the reaction. This is the half of the cell. The other half of the cell is either the reduction or the oxidation, where we're trying to measure the likeliness of that other reaction happening. We define this standard. We define this as this hydrogen electrode as the capital S, capital H, capital E standard hydrogen electrode as the mile marker or the 0 point. It's possible that the H plus of the HCl is reduced, gaining electrons from the other half of the story. It's also possible that the hydrogen gas gives up electrons to the other half of the story, depending on what else this baby is hooked up to. So if I'm referencing zinc, I'll say that zinc has actually a negative reduction potential, meaning that it would rather get oxidized. So if I hook up a zinc electrode on the other half of the story, the zinc ends up getting oxidized and the hydrogen ends up getting reduced. Yeah, the hydrogen ion ends up getting reduced, gaining electrons from the zinc and getting reduced to hydrogen gas. The E naught of reduction for that is 0. The E naught of reduction for this backwards equation is negative 0.76. But negative 0.76 is less than 0, less positive than 0. So we end up switching the zinc 2 plus 2 electrons, gives zinc solid backwards to do the backwards. That makes no sense. Or conversely, if I hooked up the chloride electrode, chlorine gas to the chloride electrode, it ends up being positive 1.36, which is more positive than the 0 of the hydrogen. So if I hooked up the chlorine chloride electrode to the hydrogen ion electrode, I would see that this is the oxidation and this is the reduction. I'm almost confusing myself. I better give some more examples. So I put a zinc strip into some zinc, 1 molar zinc sulfate. Sulfate's pretty inert. It's going to sit there. And I put the other electrode, the other half cell, as the hydrogen electrode with hydrogen gas and hydrogen ion. And as we mentioned, it comes out to be positive 0.763. But in terms of voltage, it's a spontaneous transfer of electrons. The zinc gives up electrons through this meter over to the hydrogen ions, becoming more hydrogen gas. So I'm pumping in hydrogen gas, but I'm making even more hydrogen gas as the hydrogen ion gains electrons from the zinc. Well, if that setup confuses you a little bit, let me try to simplify and say, there's another one. Setting another setup where I have the copper metal and copper ion in contact with each other, and I say, well, let's see this is spontaneous as well, isn't it? Yeah, 0.337 volts, and the electrons in this case travel from the hydrogen gas through the wire. As the hydrogen gas becomes hydrogen ion, it spits out electrons and they come over this way. And the electrons are attracting the copper 2 plus, and this electrode looks like it's getting heavier now in this case. Previously upstairs, this one, the electrode's getting, as the anode getting eaten away, as the zinc travels into aqueous solution from the metal bar, zinc metal. Anyways, let's look at these numbers a little bit more, these tables. If I have a very positive reduction potential, I call them good oxidizing agents. If it's a positive reduction potential, it wants to happen as a reduction. If it has a very negative reduction potential, it does not want to happen as a reduction. These actually want to get flipped backwards. This lithium and this cesium and potassium would be good reducing agents, giving up their electrons. In other words, they want to get oxidized. Other ways to say it, the more positive the standard reduction potential, the more likely that is to want to happen in that direction. Is bromine liquid likely to gain 2 electrons and become bromide ion? You bet it is. It'll oxidize your skin, it'll burn your skin, it'll take electrons from your skin. Bromine's nasty. On the other end of the table, these are good reducing agents. These will likely not be spontaneous in the direction written. As reductions, they want to be turned backwards, so they can become oxidations, and their negative number turns positive. So if I'm simply comparing two numbers, two half reactions, I say chlorine, chloride, bromine, bromide, and this is the simple part, whichever standard reduction potential is more positive or less negative, that's the one that's going to happen in the spontaneous direction. So this one's more positive than this one. So I leave this one alone and turn this one backwards. As I turn it backwards, the positive changes to a negative, and I see some kind of spontaneous cell potential, some kind of positive cell potential, describing the spontaneous nature of that reaction. Or if I consider iodine, iodide, copper 2 plus copper, this one's more positive, that one's less positive, so I'm going to leave this one alone, turn this one backwards, and say, could I make a copper 2 plus iodine, iodide battery? Absolutely. They're two different half reactions, or two different likely degrees of likelihood, and so this one remains as was given. This one gets turned backwards, and I write oxidation, change it to a negative. But still, if I leave the more positive one alone and turn the less positive one backwards, I'm still going to get a positive cell potential, a spontaneous reaction. What about the copper 2 plus copper, magnesium 2 plus magnesium? Sure, as long as they're different, you can make a battery out of it. Which one's more positive? This one's negative, that one's more positive, 0.34, so I'll leave that one in the direction given. I turn this one backwards, the negative 2.37 changes to a positive 2.37. Oh, I didn't even bother to write that one out. Well, you can write it if you want to. What about these two half reactions? Iron 2 plus iron, chromium 3 plus chromium. Aside from the 2 and the 3 being a little confusing, I guess 6 electrons would be transferred overall. I leave the more positive one in the direction given, even though it is negative, it's less negative than this one. I change this one backwards, turn it backwards as an oxidation, leave this one as a reduction, and the oxidation, now being positive 0.74, overcomes that negative, and lo and behold, you still have a spontaneous cell. The other twist is you could be given an equation and asked, will this be spontaneous? Well, tin 2 plus going to tin 4 plus, lead 2 plus going to lead. I sort of pull the tin 2 plus and the tin 4 plus out and say, is this likely to happen? Pull the lead 2 plus and the lead down and say, is this likely to happen? I look this up, it's a reduction where I gain 2 electrons from the lead 2 plus to become lead. That's listed in the table as negative 0.13. But this one's listed in the table backwards as a reduction. So if I'm curious to know if this will happen in this direction as an oxidation, I need to take that 0.15, since this is backwards, and make it negative. I add the two together and find a very negative cell potential. So guess what? That's not going to want to happen in a spontaneous way. So this is not spontaneous, as opposed to something like this, where I say, they give you this equation and say, is this likely to happen? Pull the cadmium 2 plus down and the cadmium down, that's a reduction, gaining electrons. Pull the calcium down and the calcium 2 plus down, that's an oxidation, losing 2 electrons. Since this calcium 2 plus calcium was listed backwards, I swap it out backwards and call it an oxidation. The negative 2.87 changes to a positive, and lo and behold, that is greatly positive, that's only a little bit negative, and so this would be spontaneous if it comes out to a positive cell potential. The smiley means it would be spontaneous. Here's one for you to work on if you'd like to pause the video and try it. Hydrogen goes to hydrogen ion goes to hydrogen gas, chromium 3 plus. The chromium goes to chromium 3 plus. Would this be spontaneous? Jeopardy music. Pause the video if you care to practice with this one. But of course you're lazy and you know I'm going to tell you the answer right now. Well, let me pull the hydrogen ion down and the hydrogen gas down and say I'm losing 6 electrons. Pull the chromium down, the chromium 3 plus ion down and say oh, goodness gracious, I should have, something's wrong here, right? Duh, oh my word, that's a big boo-boo. Hopefully you're watching this video and not just looking at the PDF. I should write the 6 electrons over here on the left-hand side. Lord, is that an oversight or what? So 6 hydrogen ions plus 6 electrons, that should be over here on this side. Go to 3 hydrogen molecules. Still, the voltage is 0 because that's part of the standard cell, like the standard hydrogen electrode. So that's a 0. That's correct, but this is a huge boo-boo. This should be listed over here. Gosh, that's embarrassing. I should change that before I post this, but what's the likeliness I have the time for that? Anyway, it's since I flipped this one backwards as an oxidation, it was negative up here, right? Negative 0.74. I flipped it backwards to be a positive 0.74. So now the 0 plus positive 0.74 comes out to a positive standard cell potential. So the answer is yeah. Have you guys seen this cell notation before? It's like the salt bridge is here, and this is the oxidation over here, and this is the reduction over here. Yeah, with the standard hydrogen electrode is a platinum piece of platinum in contact with hydrogen gas in contact with hydrogen ion in 1 molar acid solution. And the chromium electrode and the chromium aqueous, 1 molar. 1 molar, 1 molar. We're getting close to the end here. This is also a little bit of an oversight. I would have written 3 lithiums and 3 lithium ions. The spontaneous part would be to say this is more positive than this, so let's leave the gold 3 plus and the gold in place, and 3 lithium ions gaining 3 electrons to become 3 lithium, flip this backwards, 3 lithium atoms losing 3 electrons to become 3 lithium ions. But as we know, I'm not going to multiply this times 3. Interesting. The standard cell potentials don't change. But in any case, I'll leave the details to you to write out if you want to write them out. But this would be the spontaneous direction. This would be the non-spontaneous direction. It also works with water if you want to be picky about it, to say that this one could be in combination with this one, but this one would have to be turned backwards because this is less positive than this one. And when I do that, I turn this one backwards, change it from negative 0.83 to positive 0.83, and I'm gaining 4 electrons here and losing 4 electrons here, and I can, did I write out the full equation? I think I did. So this is the fundamental operation of the fuel cell, where I could take, the recombination of oxygen gas and hydrogen gas in a controlled way to harness that transfer of 4 electrons without exploding it in an explosion. I get a voltage of 2 volts, a little more than 2 volts. The non-spontaneous would be to take the water and go backwards into the 2 gases. That's not going to happen. Whew. Thanks for watching, guys. That's a long one. See you in class. Thanks for all your hard work. Keep it up.